Hello friends, Mr. Burrell here. We're getting ready to finish off this unit on statistics. We've talked a lot about setting up a study, different parts about how to identify your population, your sample, how to gather your sample so it's unbiased. We've talked about once I've organized my study, once I've set up the question that I want answered, I've talked about how to create a histogram to visualize that data. We've talked about standard deviation as a measure of how spread out that data is. So today we're going to combine that in the subject of analyzing data. We're going to combine what we know about histograms, we're going to combine what we know about standard deviation, and we're going to talk about the normal curve. So this is the last lesson we're going to talk about in relation to statistics. It's going to be on the normal curve. So by the end of this video, by the end of this lesson, this is what I hope you're able to do. I want you to be able to draw the normal curve and know how its measurements are determined, and know the empirical rule and use it to interpret normally distributed statistics. So we're going to talk about the normal curve and how it's a helpful tool in helping us to analyze statistics, analyze information, data that we've collected. Okay, so back when we were talking about histograms, I pulled up a picture of something like this. I talked about how when data is skewed, if I have a histogram like this, skewed data kind of has like a tail on either side. I have most of the information kind of shoved up against one side, and then I have a tail of data towards the other side. So like this left histogram is right skewed because it's kind of skewed to the right. I have a tail over here on the right where a bunch of my information is. And then I have this left skewed data set where there's less information off to the left, less data values off to the left, so I have a little tail off to the left. This one in the middle you would probably call normally distributed. It's not right skewed, it's not left skewed, it's pretty normal, it's pretty symmetric. You see that most of the data values are kind of here towards the middle, and they're less off towards each side. So I call a data set like this normally distributed. Most of the values are in the middle, and then less of those values are out towards the edges. So we say that a set of data follows a normal distribution when the histogram looks something like this. So you see all these histograms of a bunch of different data. You see how most of this stuff kind of congregates, most of the values kind of congregate right in the middle, right around what the average of that data set would be. It kind of centers right there in the middle, and then less of the data values are out towards the edges. Kind of see that. So most of the data values are congregated in the middle, and then less of them are out towards the edges. So where this middle point would be the mean or the average of that data set, and then the rest of the data values are kind of surrounded around that average, with more being closer to the average, less being in the tails on either end. So some definitions for you. The normal curve is a bell-shaped curve which shows the probability distribution of a continuous random variable. So when we talk about a continuous variable, that's talking about a numerical variable that can have decimals and fractions and whatever it may be. So a bell-shaped curve shows the probability distribution of a continuous random variable. Or in other words, it shows, if I were to create a histogram of a continuous random variable, it shows me approximately how those data values would be distributed. So I keep saying that word, a distribution. A distribution is a listing or function showing all the possible values or intervals of the data and how often they occur. So a distribution is basically, again, when I'm looking, if I use a histogram as an example, it's listing all the possible intervals that I could have for whether, let's use height, for example. A distribution would show all the possible intervals for height, so say from like 40 to 50 inches, 50 to 60 inches, 60 to 70 inches, whatever, and how often those values occur. It's a frequency distribution, or a frequency histogram. It just lists all the possible values or intervals of the data and how often they occur. The empirical rule, also we kind of denote it as the 68, 95, 99.7 rule. We'll talk about this in a minute, but it's a statistical rule that in the normal curve, so in this normal curve, I'll write this little bell, kind of looks like a bell, almost all the data falls within 3 standard deviations of the mean. So last lesson, we talked about the standard deviation and how a standard deviation is a measure of how spread out the data is. Right? So we're going to talk about how the empirical rule states that in a normal curve, if data is normally distributed, that basically all information, all data is going to fall within 3 standard deviations of the mean according to this rule. So let me show you here real quick. Let me erase some of this stuff. So this is a normal distribution. So again, most of the stuff is congregated here in the middle, right here in the middle, and then less of the stuff is congregated here on the edges. So notice here I have my mean in the middle, and then I have values that are 1 standard deviation above or below the mean. So those are values that aren't super far away from the mean. I have the data values that are 2 standard deviations above or below the mean. Those values are a little bit farther away from the mean. They're a little bit more uncommon probably. And then I have values that are 3 standard deviations above or below the mean. Those values are values that are pretty far away from the mean. We might consider them outliers. They're not expected. We would expect most of the values to be in this middle part. So this is where the 68, 95, 99.7 rule comes in. 68% of values in a normal distribution are going to fall in between 1 standard deviation of the mean. So almost about 2/3 really of data values in a continuous distribution, so in all these decimals and fractions of whatever we're talking about, 68% of those numbers are probably going to be pretty close to the mean, within 1 standard deviation. 95, so almost all of my values are going to be within 2 standard deviations of the mean. So between 2 below and 2 above, standard deviations below and above the mean, 95% of my data values are going to be in that range. So most of them are going to be within 2 standard deviations of the mean. 99.7, so almost 100% of my data values are going to be within 3 standard deviations of the mean. 3 standard deviations is pretty far away from the mean. We don't expect many values to be above or below that spread out. We don't expect the data to be that spread out. So 99.7% of those data values are going to be within 3 standard deviations of the mean when that distribution is normal. Or in other words, it looks like this little bell curve. So that being said, if I were to split this down the middle, right here between the mean and 1 standard deviation above the mean there's going to be 34% of my values there. And between my mean and 1 standard deviation below the mean, 34% of my data values are going to be there. Between 1 and 2 standard deviations of the mean on either side, excuse me, 13.5% of my data values are going to fall there. Between 2 and 3 standard deviations, 2.35% of my data values are going to be there. And then above 3 standard deviations or below 3 standard deviations, it's just going to be 0.15% of my data values that are above 3 standard deviations away from the mean. So not very many. You can see that most of my data values are going to be in this range. Much fewer of them are going to be outside of that. Okay, let's put this into practice. Let me show you how we can use this kind of information to approximately solve a problem. So, say there's a study, and according to the Centers for Disease Control and Prevention, so the CDC, the heights, this is a common example, the heights of 3-year-old females can be modeled by a normal distribution with a mean of 94.5 centimeters and a standard deviation of 4 centimeters. Okay, before I even read on into this question. So it says that the heights of 3-year-old females can be modeled by a normal distribution. So this is a normal distribution. I have the little graphic with the empirical rule off here to the side. And then I have this blank normal curve here. So on this normal curve, this will be the mean. This will be 1 standard deviation above the mean, 2 standard deviations above the mean, 3 standard deviations above the mean, 1 standard deviation below the mean, 2 standard deviations below the mean, and 3 standard deviations below the mean. So it says that the height of 3-year-olds, females, can be modeled by a normal distribution with a mean of 94.5 centimeters. So the average 3-year-old female is 94.5 centimeters. 94.5 centimeters is like 37 inches tall, to give you some kind of perspective. So the mean is 94.5 centimeters, and the standard deviation is 4 centimeters. So someone who is 1 standard deviation above the mean, so a little bit taller than the mean, is going to be 98.5 centimeters, because it's 4 centimeters above the mean. 2 standard deviations would be 4 more than that, so like 102.5 centimeters. And then 3 standard deviations would be 4 centimeters bigger than that, so 106.5 centimeters. And then the same in the opposite direction, over in this direction, 4 standard deviations, or 1 standard deviation below the mean is going to be about 9 centimeters less than the mean, so like 90.5 centimeters. Another 4 centimeters below that is going to be 86.5, whoops, not 88, 86.5. 4 centimeters below that is going to be 82.5 centimeters. So you can already kind of see that most of the 3-year-old females are going to be like in probably this range, between 90.5 centimeters and 98.5 centimeters. Fewer kids are going to be a lot taller than that or a lot shorter than that. For example, my son in the, they print off these forms when you go to the doctors that tell you like what percentile your child is in for height. Miles, my son, when he was 1 year old, was like all the way down here. He was like the shortest baby in the entire world. And there wasn't very many that were shorter than him. So he was like 3 standard deviations below the mean. He was like one of the farthest spread out heights of babies. Anyways, so Macy, this little girl, is 102.5 centimeters tall. So she's right here. She's 102.5 centimeters tall. So the question says, what is the probability that a randomly chosen 3-year-old girl is taller than Macy? So what is the probability that we're going to choose a girl from this normally distributed population, so all the 3-year-old girls in the world, what is the approximate probability, or what is the chance that I'm going to select someone that is taller than 102.5 centimeters? So in other words, what is the probability of, on this normal curve, selecting a value that's larger than 2 standard deviations above the mean? Well, if I go over to this curve, if I go over to my normal curve with the empirical rule, here's my 2 standard deviations. See that? And the probability of selecting some value bigger than that would be, the percentage here is 2.35%, the percentage here is 0.15%. So the probability of selecting a 3-year-old girl taller than 102.5 centimeters tall is going to be 2.35% plus 0.15%, which on my calculator is 2.5%. So the probability of choosing a random 3-year-old girl that's taller than 102.5 centimeters is only 2.5%. It's not very likely that we're going to choose at random a random 3-year-old out of this population and have her be taller than 102.5 centimeters, or larger, farther away than 2 standard deviations from the mean. Okay, let's do another one. Oh, yeah. This is number 2. I just typed the number wrong, I think. The average life of a certain light bulb is 400 hours with a standard deviation of 50 hours. Okay, so before I even move on to the question, let's draw my little normal curve. So I have a normal curve here. Again, it just looks like this little bell, this little tall bell. So the mean, the average life of this bulb is 400 hours. That's not bad, right? 400 hours worth of light. Then it says the standard deviation is 50 hours. So 1 standard deviation above the mean is going to be 450 hours. 200 standard deviations above the mean is going to be 500 hours. 550 hours is 3 standard deviations above the mean. 350, 300, and 250 are 1, 2, and 3 standard deviations below the mean, respectively. So that's about, like, not all light bulbs are going to last 400 hours. Some are going to last longer than that. Some are going to last less than that. But most of them are probably going to last between 350 and 450 hours-ish. So this says the average life of a certain light bulb is 400 hours with a standard deviation of 50 hours. What is the probability that a randomly chosen light bulb will not last past 250 hours? So 250 hours is all the way over here. Most bulbs are going to last more than 250 hours, right? If the average is 400 hours, it's probably not very likely that it's only going to last 950 hours. So what's the probability that a randomly chosen light bulb will not last past 250 hours? Well, this is 3 standard deviations below the mean. So let me go over to this graphic with the empirical rule. So less than 3 standard deviations away from the mean, so less than this, the probability of selecting a light bulb in that range is 0.15%. So the probability that a randomly chosen light bulb will not last past 250 hours is only 0.15%. It's very, very unlikely that a light bulb's not going to last that long. It's more likely that it'll last closer to 400. Okay? So because of how spread out the values of how long these light bulbs last, it's extremely unlikely that a light bulb will last less than 250 hours. Okay, so I'm going to give you a quick self-assessment, but I am going to do a homework problem real quick, one of the problems off of the homework. But I hope you're able to draw the normal curve and now know how its measurements are determined, and know the empirical rule and use it to interpret normally distributed statistics. So let's find a problem, use this problem here. And in your guided notes, you can kind of reference back to that empirical rule, that chart, so you can see those percentages. But this is question number 2 on your homework. It says students at Box Elder High School get 7 hours of sleep each night on average. So on average, students get about 7 hours of sleep each night. This data is approximately normally distributed with a standard deviation of 1.6 hours. Okay, so let's draw on our little normal curve. We have the mean, and then 1, 2, and 3 standard deviations above or below the mean. So my mean is 7 hours, and then my standard deviation is 1.6 hours. So 1.6 above the mean would be 8.6, and then this would be like 10.2, 11.8. I'm just going to add 1.6 each time. And then 7 minus 1.6, that's going to be 5.4. 5.4 minus 1.6, my brain is hurting, is 3.8. Minus 1.6 is 2.2. So on average, kids get about 7 hours of sleep. It looks like most kids get between like 5.5 and 8.5 hours of sleep, and much less kids will get like more than 10 and less than 4 hours of sleep, kind of, okay? So what is the probability that a randomly chosen student gets more than 8.6 hours of sleep? So what is the probability that a randomly chosen student gets more than 8.6 hours of sleep? Well, on my little graphic, if I kind of copy over, this is 30, this little section is 34%, this little section is 13.5%, this little section is 2.35%, and this little section is 0.15%. Same on the other side, 34%, 13.5%, 2.35%, 0.15%. So the probability of sleeping more than 8.6 hours, that's going to be 13.5. Let's see, 13.5 plus 2.35 plus 0.15. So 13.5 plus 2.35 plus 0.15, that's 16. So the probability that someone sleeps longer than 16, or longer than 8.6 hours at night is 16%. About 16% of students at Box Elder High School get more than about 8.5 hours of sleep. Okay? So out of 1,600 students, this is part B, out of 1,600 students, how many sleep more than 8.6 hours? Well, if only 16% of them do, let's multiply 1,600 students times 16% of them, or times 0.16. 1600 times 0.16, 16% of those 1600 students is about 256. So about 256 of the 1600 kids at Box Elder High School sleep longer than 8.6 hours every night. It's not very many of them compared to the 1600, right? Okay, out of 1600 students, how many sleep less than 3.8 hours? So here's my 3.8 hours. So less than 3.8 hours, I have 2.35% plus 0.15%, which is 2.5%. So 2.5% of students sleep less than 3.8 hours. That's not enough sleep, kids. So 1,600 students multiplied by 0.025, if I write that percentage as a decimal, 1,600 times 0.025 is 40. Only about 40 kids at Box Elder High School, probably close to that, sleep less than 3.8 hours each night. I'm glad it's that few because that's not very much sleep. Okay, last part here. What is the probability that a randomly chosen student gets less than 7 hours of sleep? So less than 7 hours of sleep. Here's 7. That's the mean. So before I even compute this, what do you think? What's the probability if 7 is the average number of hours of sleep someone gets per night? What is the probability that someone gets less than 7 hours of sleep? Well, let me take 34% plus 13.5% plus 2.35% plus 0.15%, 34 plus 13.5 plus 2.35 plus 0.15. That's 50%, which makes sense because if 7 is right in the middle, on this 50% of data values are going to be below that, and 50% of the data values are going to be above that. So what's the probability that a randomly chosen student gets less than 7 hours of sleep? About half. Half of them get less than 7 hours of sleep. Half of them get more than 7 hours of sleep. So again, I hope that this was helpful. I hope that you are now able to understand these objectives, draw a normal curve, and use properties of the empirical rule in association with the normal curve to approximate different probabilities. I do hope that was helpful. Let me know if you have any questions. Don't hesitate to reach out. And I hope that you enjoyed that as much as I did.